All right, let's take a look at problem 5, which is problem 12.17 from the course textbook, our next modified Raoult's law problem. And so we're told the system water phenol is described by the Van Laar equation with constants B12 is equal to 0.83 and B21 is equal to 3.22. And first in A, we're asked to construct a Pxy phase diagram. All right, so B12 and B21 are two model parameters for the Van Laar equation. And so as I peek over to my PowerPoint presentation on excess Gibbs free energy models, I use the notation in that presentation instead of B12, A12 prime, instead of B21, A21 prime, just to be consistent with using these big A's like we do in the Margulies equation. So if I flip over to our notes, here's our Van Laar equation expressions. And so the big thing to know will be if I have A12 and A21 or B12 and B21, then I have parameterized expressions for log gamma 1 and log gamma 2 as a function of composition. So those are going to be the parameters for this model. So remember, in this, which is essentially our, your problem for your problem set, we'll set the problems up, but then it's up to you to solve it at home. So the big thing will be is knowing B12 and B21 that we have expressions for log gamma 1 as a function of, say, composition x1, and we have expressions for log gamma 2, which is likewise just a function of composition. We have the actual model parameters. So let's go about constructing a Pxy phase diagram at 100 degrees C. So just as a refresher, what's a Pxy phase diagram? So let's plot a Pxy for an idealized system. We'll keep inventory of what we need. So remember, temperature is going to be fixed in a Pxy, and so that's good. Here we're told temperature is 100 degrees C. Looking at my pure component limits, that would be P1 sat, where my bubble line hits my other pure component limit. This would be P2 sat, and then here's my dew line. Bam. All right, so looking in terms of pure component properties and properties that I need. So we have temperature, saturation pressure phenol at 100 degrees C is 0.055 bars. So we have P2 sat. P1 sat, we're not given, but we know that at 1 bar, water boils at 100 degrees C. So in theory, then I have P1 sat. And so remember, it's not given because essentially we know that at 1 bar, water boils at 100 degrees C. So at 100 degrees C, which is the temperature of interest, we know that P1 sat, is equal to 1 bar. Cool. Approximately 1 bar. 1 ATM, 1.01325 bars. So we have our vapor pressures, we have T. So life is good. How do I go about constructing a Pxy? Well, I'm going to think about it in terms of, Excel. So if I were setting up an Excel sheet, I have some cell, I've got B12, I have B21, I've got my Van Laar parameters, I have P1 sat, I have P2 sat, and I could put temperature in a cell too, Even though I don't explicitly need temperature, remember the purpose of temperature is that P1 sat and P2 sat are only functions of T, So it's equivalent of knowing T in this case. All right, so as I make an aside over here by my phase diagram, so remember my criteria of phase coexistence, are my isofugacity equations. And so here I'm going to use a modified Raoult's law equation. Y1P is equal to gamma 1 x1 P1 sat. Y2P is equal to gamma 2 x2 P2 sat. Where gamma 1 and gamma 2 are only going to be a function of composition, because I have B12 and B21. All right, so now we're going to think about the algorithm in which I would go mapping out a Pxy. So if I look at my Pxy, I know I'm going to cover compositions from 0 to 1. So this is my phase diagram for an idealized system with a straight bubble line. Okay, so for this case, I know my pressure is going to be between P1 sat and P2 sat, but that's not going to be the case for a non-ideal system, right? So if I were to have, say, positive deviations from Raoult's law, right, I might get a pressure that is greater than P1 sat. Okay, it's only for an idealized system that you're going to be bound between the two. And so when I think about, say, looping over, range to solve my isotopic acid equations for each case, typically I'm going to loop over composition, and I'm going to loop over composition x1. Why? Because I know that no matter what, all of my data points are going to be bound between, these two limits, 0 and 1. Then x is typically preferred because my activity coefficient functions are going to be functions of composition, right? My liquid phase composition. All right, so the general strategy is going to be then, if I'm thinking in terms of an Excel sheet, if I'm setting up a table, I'm going to first create a column of x values that go from 0 to 1. Okay, and if I want to, I could compute x2, right? x2 is just 1 minus x1. Okay. Then the next thing I would go ahead and compute is gamma 1 and gamma 2, right? I see gamma 1 and gamma 2 are going to be here in my isotopic acid equation. Okay, and since I know B12 and B21, right, they're only a function of composition. So for a given composition, gamma 1 and gamma 2 are therefore fixed. Right? So I can add to my table, I can calculate gamma 1 and gamma 2. All right, so then how do we proceed? Well, if I wanted to, look at this system of equations, okay, so if I'm looping over x values, so for a given x, all right, I know x1 and x2, I know gamma 1 and gamma 2, right, I just computed them because they're only functions of composition. P1 sat and P2 sat are given and known. So I have a system of two equations with two unknowns. So in theory, I could just simultaneously solve this system of equations, right? Cool. And so if I were using, say, MATLAB, I could just use an fsolve command to simultaneously solve for y1 and p. Or if I wanted to, if I'm thinking about Excel, I could go ahead and just do a bubble p calculation, right? And so the easiest approach would be to do a bubble p calculation in which I were to add these two equations together. So if I add them together, p is constant, y1 plus y2 is 1. And so I just get p is equal to gamma 1 x1 p1 sat plus gamma 2 x2 p2 sat. Right? There's no need to solve it numerically when I can just simply solve it analytically. So if I do a p-bubs calculation as such, and I look at my sheet, my Excel sheet, this table I'm setting up, I know x1, I know gamma 1, I know p1 sat, I know gamma 2, x2, and p2 sat. So that would allow me just to go ahead and calculate p. Okay. Then last, how do I get y1? Well, the easiest thing would be, now that I have p, I can just go back to one of my isotopic acid equations and solve for y1. So y1 would be gamma 1 x1 p1 sat divided by p, right? Where I just solve for p. Gamma 1 x1 p1 sat plus gamma 2 x2 p2 sat. So once I have p, then I can just solve for y1. Then if I want y2, y2 is just 1 minus y1. Okay, I have everything. Then once I calculate all the data, if I want to construct a pxy, well, I plot p versus x1, this row versus this row, and p versus y1, this row versus this row. Right? I have everything I need. I can go ahead and plot out my Pxy phase diagram. Okay? Cool. All right? So that's it. All right? That's it for that part. Then in B, essentially knowing this Pxy, we're gonna solve a flash problem. Okay, so that's constructing my Pxy. So then in B, we're gonna have a flash problem. Right? So I'm just going to draw my picture so we can make sense of what we have first, right? So I'll have some inlet stream, right? Say of flow rate or amount F. I'll have some inlet composition Z1 coming off the top of my vapor stream, flow rate V, composition Y1, coming out the bottom, be some liquid of composition X1. This is going to be my equilibrium contact. It's some T and P. Presumably it's 100 degrees C, so we can just use our Pxy phase diagram. Okay, then let's label what we have. If a solution that contains 65% by mole water is flashed to 0.5 bars at 100 degrees C, what is the composition in relative amounts? Okay, in relative amounts of the phases. Okay, and so remember the book essentially always assumes F is 1. So when they compute V and L, it's relative to F, which is, just 1, right? It's all relative. So Z is 0.65. Z is 0.65. Bam. P is 0.5 bars. Okay? And so we're asked to solve for Y, X, L, and V. Okay? So now the key to this is, what relevant equations do I have? Well, I have a binary system, so I can write down two mass balances. Okay, so let's say F is equal to V plus L. And then Z1F is equal to Y1V plus X1L. All right, I can write down my two mass balances. Okay, so we'll call that equation 1 and equation 2. And then I have two isophagasity equations. Okay, so using modified Raoult's law, I'll have Y1P is equal to gamma 1 X1 P1 sat. Y2P is equal to gamma 2 X2 P2 sat. Okay, 3 and 4. And then to be rigorously correct, since I have Y2 and X2 in here, I can use my constraint equations. The Y2 is 1 minus Y1, and X2 is equal to 1 minus X1. Equation 5 and 6. Okay, so I have 6 equations. Okay, well, how many unknowns? Okay, now since we're just asked for relative amounts of L and V, remember the trick. Well, the trick that your book always uses that isn't explicitly mentioned is you just take a basis of F is 1, right? So you have to define the extent of your system before you go and solve for L and V. And since we only want relative amounts, we'll just normalize with respect to F, which is just 1, right? And so it's all the same. So if I take inventory of what we have, okay? So if I look at equation 1, okay, actually let me try and change the colors as I check, all right? So we have F, okay, V and L we don't know, we're trying to solve for them. Equation 2, I have Z1 and F. I don't know V and L, nor do I know Y1 and X1. Okay, going on to equation 3, P, I know P, it's 0.5 bars. Okay, and actually let's keep inventory. So we said V and L are unknown, and then we added Y1 and X1 in equation 2. So looking at equation, oh, that was equation 2. So in equation 3, I know P, I don't know X1, okay, so we already accounted for that. Now, in theory, I don't know gamma 1, okay, but remember, gamma 1's only a function of X1, okay, so I'm not going to list it. In theory, I could create an equation 7 and 8, which are our expressions for gamma 1 and gamma 2, but I'm not going to go crazy, okay, so I'm not going to add gamma 1 to my list, because once I have X1, I have gamma 1, okay. In P1 sat, I know. Okay, but again, if you wanted to, you could list your expressions for gamma 1 and gamma 2 here. You'd have two more equations to get those two unknowns. Okay, then I have Y2 and X2 as unknowns in equation 4, and then I've got my two constraint equations here. Okay, so if I sum everything up, I have 1, 2, 3, 4, 5, 6. I have 6 unknowns, 6 equations, so I can simultaneously solve those 6 equations for 6 unknowns, right? And then you have it. Okay. Now, since this is a binary system, we can systematically go about it. and it's not all that big of a deal. So for example, right, so since I know P, I just don't know Y1 and X1, I could start with the bubble P calculation, right? So this is just an example. So remember, what you need to do is you have a system of 6 equations with 6 unknowns that you could solve, okay? But if you want to think about these things systematically, I might start, since this is just a binary system, with the bubble P calculation. And so what I mean by that is if I write down my isofugacity equation, Y1P is gamma 1, let's write gamma first, gamma 1 x1 P1 sat, Y2P is equal to gamma 2 x2 P2 sat. All right, add these together, I get the P is gamma 1 x1 P1 sat plus gamma 2, and I'm just going to plug in for x2, 1 minus x1. All right, plug in equation 6 times P2 sat. Okay, so I know P1 sat and P2 sat. Gamma 1 and gamma 2 are only functions of x. And so I could go ahead and I could take my bubble P equation and solve for x. Right, cool. Once you have x1, you have x2 via equation 6. Once you have x, then I can get y, because y, I just go up to one of these two equations, and a y1 would be gamma 1 x1 P1 sat divided by P. So once I get x, so I get x1, okay, then I can get y1, okay, and then of course you get x2 and y2 via equation 5 and 6. And then once you have those, then you could just have to go up and solve your mass balance, right? And those you could solve simultaneously, or those you could set up to solve sequentially. Okay, so it's not that bad of a problem. It's just when you come to problems like this, advice is draw your flash drum so you get a handle of what you have, and then just writing out all the applicable equations. Mass balances, binary system. I have 2 mass balances. Number of mass balances is equivalent to the number of components in my system. Then your isofugacity expressions, right? The number of isofugacity expressions is also equal to the number of components in your system. And then here I wrote our constraint equations, just that our mole fractions have to sum to 1. Okay, cool. That's it. If you wanted to add constraint equations, your activity coefficient expressions, you could do that as well. And that would have been equation 7 and 8, at which point gamma 1 and gamma 2 would have been 2 more unknowns. I would have had 8 equations and 8 unknowns. Okay, but that's it.